Hi and welcome to John's Maths book. In this video, we're going to be looking at finding the volume beneath the surface using double integration. If you like the video, then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. In a previous video, we looked at how we calculate the area under a curve using integration. We looked at a function y is equal to f of x, and we summed infinitely small slices under the curve along the x-axis. Each of the slices was of width dx. We did this by integrating along the x-axis, and in this case on the left, from a to b. This gave us the area under the curve over the range a to b. And as you can see, this area is shaded in green in the diagram on the left. Now we want to take this a step further, and we can use integration to calculate the volume under a curved surface. Our surface is a function of both y and x. So in our diagram on the left, we now have a new axis, z or z, depending where you come from. And z is a function of x and y. So what this means is if I plug in values for x and y into this function, it will give me values of z, which will equate to points on the pink surface shown. So effectively, this gives us the height of the shape. I've now marked points A and B on the x and y axis. These points form a rectangular shape in the xy plane. If I extend the lines up to meet the curved surface, as I've done in the diagram, then the volume now enclosed by this and under the curved surface is the volume which we're attempting to find. If we now take a fixed point on the y-axis, shown as C on the diagram, how would we go about calculating the area shaded in blue? We know that our function is given by f of xy. So each change in the value of x would give a different value of z. If we now take a tiny slice along the x-axis, so dx, this will give us a tiny slice of the area of the blue shaded region. If we add up all these tiny slices of area, we get the total area defined by the blue shaded area. We do this by integrating our function f of xy from 0 to a by dx. So that's along the x-axis. Once we've done this, it'll produce a function of y. If we then plug in different values of y along the y-axis, this will generate different slices of area. So now if we take a slice of area and multiply it by a small change in y, so dy, we get a small slice of volume under the surface. I've shown this on the diagram on the left. If we then sum the small slices of volume across the y-axis, we get the total volume under the curved surface. Again, we do this by integration. So we've already integrated to get a small slice of area shown previously. We integrated along the x-axis from 0 to a of our function f of xy by dx. This gave us a small slice of area. If we now integrate along the y-axis from 0 to b, so we take the integral from 0 to b of the integral from 0 to a of f of xy dx by dy, we will get the total volume under the surface. It's not important whether we integrate along the x or y-axis first. Either way, we could achieve the same results. So in the diagram, I've integrated along the x-axis first from 0 to b. So I've taken the integral of 0 to b of our function f of xy by dy. This will give me a slice of area shown by the blue shaded area. If I then integrate from 0 to a along the x-axis, this will add up all those slices of area to give me the total volume under the curved surface indicated by the pink area. Now let's look at a real example. On the left, there's a surface which maps to the function z is equal to x times y squared. We want to find the area beneath the surface between the points 1 and 5 on the x-axis and 0 and 2 on the y-axis. So we want to integrate xy squared from 1 to 5 across the x-axis and then integrate again from 0 to 2 across the y-axis. So let's first do the x integral. So we're going to integrate from 1 to 5 xy squared dx. So in this case, the y term is a constant, and the integral should give us a function of y as we saw in the presentation. So if we integrate x, we get x squared over 2 times y squared, a values of x between 1 and 5. So if we put our value of 5 in for x, this gives us 25 divided by 2 y squared minus, now if we put our value for x equal to be 1, it becomes minus a half y squared. Then if we subtract those two fractions, we get 24 divided by 2 y squared, which is equal to 12 y squared. So this will give us a slice of area under the curve for any value of y. So now we want to integrate in the y direction from 0 to 2 of 12y squared dy. So this will allow us to add up the slices of volume in the y direction and eventually give us the volume under the surface. So if we integrate this, it gives us 12y cubed divided by 3. And we want that between y is equal to 0 and y is equal to 2. So this is 4y cubed from 0 to 2. So if we plug these values in, we put 2 in, we get 4 times 2 cubed is 8. And if we put the 0 value in, we just get 0. So this gives us a value of 32, which is our volume under the curved surface between the values of x is 1 and x is 5 and y is 0 and y is 2. Now during the presentation I said we could do the integral across the x-axis first or the integral across the y-axis first. So let's demonstrate that we can actually do that. So this time we want to integrate from 0 to 2 xy squared dy, and then we want to integrate from 1 to 5 the result of this function, which will be a function of x, by dx, so along the x-axis. So let's integrate along the y-axis first. So from 0 to 2, xy squared dy, we integrate this, we get xy cubed divided by 3 from 0 to 2. So if we plug in the value of 2 for y, we get 2 cubed, which is 8, multiplied by x, divided by 3. And if we plug in the value of 0, we get 0. So we're left with a function 8x over 3. Now we want to integrate that. So we integrate from 1 to 5, 8x divided by 3 along the x-axis. So if we do that, we get 8x squared divided by 3 times 2. And that's from the values of 1 to 5. So that equals 4 divided by 3 x squared between the values of 1 and 5. So if we plug the value of 5 in for x, we get 4 times an x squared. So 5 squared is 25 divided by 3. And we want to subtract the value when we put 1 in for x. So that leaves 4 divided by 3. So if we take the 4/3 out of this expression, we get 4/3 multiplied into 25 minus 1, which is equal to 4 times 24 divided by 3, which gives 3 into 24 goes 8 times. So 4 times 8 gives us 32, which is the same answer as we had when we integrated along the x-axis first.